All right.
One second, Professor. Please wait. Good evening, everyone. Welcome to another session of the Network Seminar Series hosted by the Center for Network Intelligence at the ECB and RPCCPS IISc. It is my pleasure to introduce today's speaker, Professor Sidharth Jaggi, and he will be speaking on the capacity of Causal Adversarial channels. Professor Sidharth received his BTech from IIT Bombay in 2000, his MS and PhD degrees from Caltech in 2001 and 2006 respectively, all in Dublin. He spent 2006 as a postdoctoral associate at Leeds, MIT. He joined the Department of Information Engineering at the Chinese University of Hong Kong in 2007 and the School of Mathematics at the University of Bristol in 2020. His interests lie at the intersection of network information theory, coding theory, and algorithms. His research group thus calls itself the CAN unit. Codes, algorithms, networks, design, and optimization for information theory team. Examples of topics he has dabbled include network coding, sparse recovery or group testing, covert communication, and his current obsession with adversarial channels. Before we move on to the talk, we would like to request the audience to subscribe to our Google group for more information on our future talks. You can also visit our website for more details. I will be pasting the links in the chat box. Please do check. Finally, we request the audience to keep your microphones on silent for the duration of the talk, except when asking questions. And for questions, please feel free to unmute yourself and ask directly or type them in the chat box, and we will relay your questions. Over to you, Professor.
Thank you. Thank you for the invitation. About questions, yeah, please feel free to ask right in the middle. No point keeping it till the end. And in case I miss a message in the chat box, please let me know. Srinivas, yeah.
Sure, Professor.
So as hopefully my screen is appropriately shared, you can see the title. This is older work presented at ISIT 2022. The bulk of it was presented there, though there's been other stuff folded together to tell a larger story. Also, apologies in advance. Yesterday morning I came down with some nasty bug, vomiting, the whole works. So I'm making my excuses in advance in case I'm incomprehensible or it's things aren't great. All right, so again, credit where it's due. This is work done jointly with my then student, my ex-student Yihan Zhang, who's currently a postdoc in Austria, and my frequent collaborators Mike Langberg and Anand Sarwate. So the capacity of causal adversarial channels, this is really the capstone to a really long line of work that we started probably back in the late in around 2005, 2006, and it's finally taken this long to get to a fairly general answer. So it's work that I'm really proud of. It's quite technical, I'll say that up front, but it's some of the work I'm happiest with in my career so far. So adversarial channels. So what's the setting? Alice over here wants to talk to Bob, but there's a jammer, James, somewhere in the middle. So Alice has this message that she transmits, and this transmission is somehow observed by James as well, who then gets to introduce an error in the transmission that is then eventually observed by Bob, who then wishes to infer what Alice had been saying, right? And often in these settings, the model implicitly being considered is that the jammer is omniscient. That is to say, he gets to see the entire transmission in advance, knows precisely what is going to be transmitted, and then thereby decides how to jam the transmission. Now, that of course can be quite unrealistic in some settings. So in today's talk, we'll be looking at so-called causal or online adversarial channel. So Alice transmits something like maybe one symbol. James gets to see it, decides how to add some noise. Then Alice transmits her next symbol. Again, James sees it, decides how to add some noise, and so on. So hence the name causal or online, right? So James doesn't know the future. He only knows what's being transmitted. Of course, here we'll assume that if there's a code book, if there's a communication strategy, then that's known in advance to all parties, to Alice, to Bob, and to James. But the specific code word being transmitted, the specific communication setting, like a specific actual transmission, that's not necessarily known in advance to either Bob or James. Yeah. And why does this matter? Well, because in the omniscient setting, James the jammer could see precisely what the transmission was and therefore could decide how to tailor his jamming attack. Oh, I'll need to put some more power here, some less power here is okay, and so on. Whereas in the causal setting, a priori, that's not necessarily obviously true, right? He doesn't necessarily know what's coming in the future, might use up too much of his power, so he'll have in general a power budget, and he may use up too much of his power in advance and then not be able to do much, right? That's his problem. So that's why causal channels, we can hope, would have a different capacity, would have a different sort of characterization than a omniscient channel. So the bulk of this talk I'll actually be giving via two examples. Even though the headline result is a general result, I'll be giving the talk in terms of two simpler channel models where many, but not all of the ideas are, come through. So so one example is a causal binary erasure adversary. So what is this adversary? What is this channel model? So Alice gets to encode a message into a code word that she transmits. The adversary sees the transmissions bit by bit, and then gets to decide whether or not to erase them, with the caveat that over n of Alice's transmissions, James can only erase a p fraction, so at most np bits, right? And then the decoder attempts to decode. So it's known that the capacity for this adversarial erasure channel is 1 minus 2p, so when p is less than a half and 0 otherwise. There's a converse idea which will outline, and achievability given via stochastic codes. So what are stochastic codes? So stochasticity basically means that the encoder is allowed to use some private randomness that's not known in advance to anyone, to the adversary, to the decoder. There's just some private randomness. So in general, depending on the particular coding scheme one uses, the capacity results can be affected. So in particular, actually, just a second. Let me just, yeah, okay, fine. I thought it was the wrong set of slides, but it should be fine. Okay. So depending on the particular coding scheme, you could have deterministic encoding, that is each message corresponds to a single transmitted code word. Or you could have a stochastic encoding that is based on the message, and then some private randomness, then Alice decides to transmit one of several possible different transmissions, one of several possible different code words. So that's stochastic encoding. So for example, in a erasure channel with a 1-bit delayed adversary, so what's a 1-bit delayed adversary? So the adversary has only seen the transmission up till time I minus 1, and then has to decide whether to erase the current bit xi or not, without seeing xi. He'll only get to see xi in the next time instant. So that's why he's got a 1-bit delay, right? So in this setting, the deterministic coding is known to have a capacity of 1 minus 2p plus, so again 0 when p is greater than a half. On the other hand, if we allow stochastic encoding, then we can show that the capacity is 1 minus p. So just the single bit of lack of foreknowledge, or single bit of delay in knowing what's being transmitted, can have a significant impact in the overall scheme, in the overall throughput of the scheme. Yeah. So that's why stochastic encoding is important. So yeah, in general, like in a stochastic encoding scheme, you have a bunch of messages, you have a bunch of private keys, and the specific code word transmitted depends not just on the message, but also on the private key. It's known in advance only to the transmitter, not the receiver, not the jammer. All right. And just some technical remarks. So one could focus on at least two different metrics. Like we could be satisfied with the average probability of error metric, which is to say that when you average overall messages and keys, the probability of error observed by the decoder, like that, would be average probability of error metric. On the other hand, a maximum probability of error metric would be maximum overall messages, average over the keys. That's what we would call a maximum probability of error metric. So in an average probability of error sense, well, most of the time, if the average probability of error is small, most of the time the messages will get through. With the maximum probability of error metric, every time the message will get through with high probability over the keys, right? So clearly this is stronger, would be more desirable from an achievability perspective. So oh, this is flipped. This is flipped. I apologize for the typo. We study achievability under the oh, sorry, my mistake. This is correct as whatever. So of course, the maximum probability of error metric is a stronger probability of error metric. So maybe a higher throughput could be attained under an average probability metric. Whereas, so for this reason, our achievabilities will be under an average probability of error metric and impossibilities under a maximum probability of error metric, right? So the strongest in both senses. And we'll show indeed that these two coincide. So, so changing the probability of error metric won't make a difference over here. All right. So for this example, for the example of the adversarial erasure channel, so let's look at some ideas involved in proving the converse and showing that you can't hope for a rate higher than 1 minus 2p. So, so here's one thing that James can do. So here I'll just outline a possible jamming strategy that James, the adversary, can use, and show that under this particular choice of jamming strategy, a rate no higher than 1 minus 2p, p is less than a half, can be attained. And we'll call the strategy a wait and push attack. So what is the wait part? Well, in the wait part, for a certain amount of time, let's call it L, James will do nothing whatsoever. He'll just sit there quietly listening, waiting, learning. So therefore, he's conserving his erasure power. He's conserving his ability to do erasures for later, when after he's learned a certain amount. And then in the push phase, that's when he'll actually begin to attack, begin to erase certain bits carefully. So, what do we want? We want that there are two different messages, u and u prime, which are different, such that their overall Hamming distance, the Hamming distance for the corresponding code words is small, right? That's what James would want for him to be able to jam correctly. Now, of course, so we are interested in a stochastic encoding strategy. So each message can map to different code words with different probability. So even if he knows the transmitted message in advance, it doesn't necessarily mean he knows the code word. So that causes some technical challenges in proving a converse. So here's how he'll work. So James will first just listen for a prefix of size L, and I'll specify what L is in a little bit. So that's a parameter of James's attack. I'll specify what that is in a little bit. But initially, he just waits, and no erasures. In the push phase, he then attempts to push x towards x prime by raising bits. So what does that mean? It means whenever x and x prime are different, he'll just erase the locations where x differs from x prime. Now, what is this x prime that James is going to use that he'll try to confuse Bob with? So, based on the observed prefix, so based on this prefix that he's seen so far, James constructs a list of candidate code words from the code book. So this is compatible. So this is the set of all possible code words. My mouse is extra sensitive. So this is a list of all possible code words that are compatible with the prefix x, x under x less than L, right? All the code words that have the same prefix. And then he just picks some x prime uniformly at random from this set. And then whenever this x prime differs from x, so he erases the evidence. So Bob, of course, wouldn't be able to know whether x was being transmitted or x prime was being transmitted, right? And if he's able to succeed in this, that is to say, if James has enough bit flips left to be able to erase all evidence where x and x prime differs in the push phase, then he will have succeeded in confusing Bob between x and x prime. Now, there's a couple of issues here. Firstly, it's not clear that he'll have enough bit flips left. Like, why should he have enough bits to erase? Because he can only flip a fraction p bits. Why does he have enough power to cause maximal confusion? That's one issue. The other issue is that, because it's stochastic encoding, maybe x and x prime happen to correspond to the same message, right? The same message could have two different encodings, x and x prime. So those issues are dealt with over here. So firstly, we can show. So firstly, the choice of the parameter L, the weighting parameter L. So firstly, we can show that if the rate is larger than 1 minus 2p, so if it's above the purported capacity, so if it's larger than 1 minus 2p plus epsilon, then there'll be a large amount of message uncertainty. There'll be a large number of messages. So the entropy of the message conditioned on the observed prefix is relatively large. It's linear in n, so it's larger than n epsilon by 4 at least. Yeah. So because of this large message uncertainty, therefore, you can show that with high probability, when James picks a random x prime, the code word x prime will correspond to a different message than the true message m that Alice has chosen. Yeah. Next, we can show that with some constant probability, with some positive probability, so not probability close to 1, but not probability close to 0 either, with some constant probability, x prime is not too far from x. So what does not too far mean? Well, it will mean essentially that for these parameters, for the parameter choices when r is 1 minus 2p plus epsilon, the L that we'll specify in just a little bit, and the fact that he can erase at most NP bits, that he will indeed be able to confuse Bob. He will be able to erase all the locations where x differs from x prime. So in this case, we'll choose L to be basically the capacity plus epsilon over 2, and then we can show that the probability. So what was E1 again? Yeah, I apologize. I'm still a little bit out of it because I'm still a little bit sick. I would have reviewed this a lot more carefully if I wasn't sick. But anyway, so E1 is the event that the prefix is somehow typical. So it's in the set of code words which have large message entropy. So the first lemma just is essentially it's essentially like a Markov lemma, like a Markov inequality. So with some information inequalities thrown in, so you can show that with reasonable probability there'll be large message uncertainty. Then step 2, picking a spoofing code word x prime, erasing bits where they differ. So here you can show via modification of Fanov's inequality that the probability that m and m prime correspond to the same, so x and x prime correspond to the same message. Well, that is actually that event is bounded away from 1. In particular, the probability of that happening is no more than 1 minus epsilon to the 1 over epsilon. Now, epsilon to the 1 over epsilon is a very small constant, right? But the important thing is it's a constant that's strictly positive. And therefore, with this probability, there'll be the m and m prime will differ, will correspond to different messages. And therefore, when Bob is confused between x and x prime, he'll be confused between different messages, m and n prime as well. Some other technical challenges, the private key may be non-uniform. So I'm not going to go too deeply into that, but there are some technical challenges involved in trying to prove a very general converse. So the idea here is we sort of decompose the private key in a suitable manner, so that, and then treat the decompositions as separate private keys. So eventually you can always quantize private keys down so that they're quasi-uniform, and then the proofs sort of go through anyway. All right. So finally, to show that James will have enough bit flips to be able to, enough erasures handy to be able to confuse Bob between x and x prime, the idea is to basically use something like a Plotkin bound. So a Plotkin bound, for those of you who studied some coding theory, says something of the following kind. It says that given any sufficiently large code, there'll always be a pair of code words. So if you demand that the minimum distance be larger than half the block length for binary codes, then there'll always be a pair of code words such that their Hamming distance is essentially half the block length, is essentially n over 2 times 1 plus epsilon. Now the average Plotkin bound says essentially the same thing, except instead of saying there'll be one pair of code words, you can basically say that if you sample pairs of code words, then with constant probability, again, the sampled pair will have Hamming distance at most NP, right? So so it's an average version of the Plotkin bound. Instead of focusing on the closest pair, it'll make essentially the same statement with constant probability for randomly chosen pairs. So so that's basically the high level idea for the converse. Let's move now to achievability. So achievability goes by, well, for achievability, we have to show an encoding scheme that Alice can use. Excuse me. So for an achievability, as we said, Alice can use private randomness. It can use stochastic encoding. And again, this is only known to Alice, not known to the decoder, not known, of course, to the jammer James. So now, if Alice does this naively, and what I'm calling naive stochastic encoding is, so for each message, there's a bunch of possible private keys. So let's choose these code words as random, which is what we usually do in information theory, right? We choose code words at random. So for each message, if we choose code words at random, the second message could choose code words at random, and so on. So so if there are k bits of if there are k keys, so log k bits of private randomness, then with relatively standard arguments, you can see that after weighting roughly nr bits corresponding to the message entropy plus log k bits corresponding to the key entropy, then with high probability after weighting this long, James will have learned not just the message, but will have learned the full code word, because the overall entropy of the transmissions is at most the entropy of entropy of the messages plus the entropy of the keys. That's this much. So by relatively standard arguments, waiting this long will have told James everything. Now, of course, you can make the key have a much larger entropy as well, but that comes at a cost because the key, remember, Bob, the decoder, also doesn't know the key. So he may have to learn something about the key to be able to decode the message. So therefore, increasing the key to be a lot also may not be a good idea, right? So this sort of a naive encoding strategy may not be a great idea. So that's why we do something called so we do something called chunk-wise encoding. So so let's choose some parameter theta, which is small. It's like epsilon over 3. Epsilon, remember, is a backoff from capacity. So some small parameter. And now we'll break up our transmission into a large number of chunks into 1 over theta chunks, each of length n theta. So in every transmission, in every chunk, just n theta bits will be transmitted. Think of it as like some constant times an epsilon number of bits will be transmitted. And for every such chunk, the message plus a small number of random bits. So will be mixed together to create a code, chunk code word, also of length n theta, also of length n theta. And then, we'll repeat this multiple times. We'll repeat this 1 over theta times to create the full code word to be transmitted. Now, critically, these private keys over here, S1, S2, all the way till S1 over theta, will be chosen randomly and independently. So each of them is not going to be very large. Each of them will be some function of theta. I think theta cube is what we've chosen. So each of them will have a small amount of private randomness, but the randomness used in a given chunk will be independent of the randomness used in the next chunk, right? So the overall concatenated structure will look like the part of the code word corresponding to the message and private randomness 1, message and randomness 2, and so on. Now, what's the advantage of doing it this way? So yeah, we can concatenate together, transmit the whole thing, and we have an n-bit transmission. So yeah, so also some parameters. So there'll be some choice n prime and chunk number t, so that r plus n plus yeah. So remember, k is the number of okay, right. So actually, wait, let me just jump ahead. Yeah. So first, let's give some intuition as to why this chunk-wise strategy is a good idea. So in the naive stochastic encoding setting, if you remember, after nr plus log k bits, James the jammer would have been able to learn the transmission. But over here, so after every n theta bits, it's as if James has to start all over again. So even if he's learned the message, there's still going to be something like 2 to the n theta number of, or 2 to the n theta cube number of possible transmissions just for this short chunk. So he'll always be somewhat uncertain. He'll always be somewhat uncertain as to what is coming down the pike, right? At this point, it could be here, it could be here, and so on. So because he's always a little bit uncertain, therefore he can't plan in advance. He can't decide, oh, I want to use more bit flips in this chunk, less bit flips in that chunk, and so on. So that's what will give us an advantage. By the way, I should say in advance, these slide numbers are misleading. This is a mash of multiple talks. There are going to be more than 20 slides, so I forgot to remove those. Yeah. Right. So just some parameters to specify how the encoding will work. So the yeah. So let's say k. Yeah. So let's choose. Let's figure out the first time when the number of message bits plus plus k. So I claim there'll be a chunk number t, which will where the following will happen: the number of bits plus the erasure so far plus some very small slack. So remember, theta is a very small slack, is less than n prime. So this condition over here is basically saying that the overall observed entropy, by Bob, which is the number of unerased bits plus no entropy from the erased bits, will be equal to the number of received transmissions by Bob so far, right? So like every time a bit is not erased by James, well, then some amount of entropy gets through to Bob. So eventually, since James can only erase np bits for p, some constant fraction p, then eventually this condition will hold. There'll be a certain point at which there'll be enough entropy for this condition to hold, and therefore for Bob to be able to list decode. So that's why this comes into play. And then in the subsequent chunk, so here's another high-level key idea. So for our choice of parameters, we'll be able to show that there'll be a chunk in the future where James will be able to erase relatively few bits. He'll be able to erase slightly less than, at most, slightly less than half the number of bits in that given chunk, Okay, so let me just repeat very quickly. So basically, Bob's decoding strategy will be to always wait until he at least gets enough entropy to be able to, in principle, try to decode. But just having enough entropy is not enough. In these adversarial coding problems, like just because the entropy of the received vector is sort of close to the message entropy, it doesn't mean that you can uniquely decode. In these adversarial communication problems, there may nonetheless be at least a small number of code words which are all compatible, a small number of messages which are still compatible with the observation. So you'll need some future transmission to help disambiguate between these. And so in the prefix, so you have enough entropy to get it down to a small list. That's what's called list decoding. So you can ensure that Bob can infer, oh, that at most a small number of possible messages, and then he'll use the information from this chunk in the future, which has a relatively small number of erasures, to say, of the small list that I've been able to whittle it down to, this is the actual transmission that was intended by Alice. Yeah. So all of this slots together nicely, specifically for the choice of parameters that we've chosen, which is, so the rate we chose is 1 minus 2p. The rate we chose is 1 minus 2p. So since we chose a rate of 1 minus 2p, the suffix length, so since we chose a rate of 1 minus 2p, therefore the prefix length is, so you can imagine the setting where just as a thought experiment, let's imagine no erasures happened in the prefix. Yeah, that corresponds to James's wait and push sort of attack. So then the suffix length would be 2p times n, right? And therefore, on average, you'd expect at most half erasures per chunk, right? Now, if you just back off by epsilons here and there, so if you just reduce the rate to 1 minus 2p minus epsilon, then there'll be at least one chunk in the future which has slightly more than half erased bits, right? So this this gives intuition as to why 1 minus 2p is the right answer for the erasure channel, and there'll be similar versions for other channels we'll see as well. Yeah. Right. So we've already talked about this. So Bob waits until he can figure out when he can hope to try to decode or try to list decode, outputs a small list. So typically, while list decoding, you can see you can get these list sizes down to a constant size. So this list size is going to be order 1 over theta. Remember, theta is a small constant. So order 1 over theta is a large constant, but nonetheless still a constant. Independent of the block length n, and then Bob will be able to locate this chunk over here where relatively few erasures had happened, right? And then use that to try to disambiguate, try to figure out what was happening. Yeah, so we've already talked about this. So based on that particular chunk, he'll then look at all of the possible messages in the list from the prefix and check for consistency. But what does checking for consistency mean? So for this particular message, looking forward in the future, depending on all possible keys that Alice could have used, there would have been the list of all possible code words that could have been transmitted in that chunk, right? So if it was message I, again, a typo, this should be message 1. So if this was message 1, then there would be a corresponding list of possible code words in chunk T prime corresponding to the key 1, corresponding to key 2, key Sj, corresponding to key 2 to the n times S, right? So this is the list of all possible code words corresponding to message 1 in chunk T prime. Similarly, you can do the same thing for message I, for message L, for all of these messages, you can do that. And now look at all of these, possible completions in chunk T prime and check, well, do any of those match what I'm actually observing in chunk T prime? And since chunk T prime has quote unquote relatively few erasures, has strictly less than half erasures, so you can argue, you can show that in fact, with high probability, only one of these completions will match what is observed over there. Yeah. So yeah, there's some examples given over here, which I'm not going to step through. let's see. Yeah. So there's some technical things that one has to worry about over here. So think about for each so Bob obtains a small list of messages with high probability in that first phase. Again, that's relatively standard list decoding with some technical differences because of this chunked nature of our code book. But other than that, it's a relatively straightforward list decoding result. Now, each message corresponds to exponential number, a small exponential. So this S, think of that as some function of theta, think of that as theta cubed. So it corresponds to a small exponential number of possible subcode words within that chunk. And if James gets to erase like a strictly less than half fraction of bits in that chunk, then, well, he can cause some confusion, right? So in that chunk, maybe this was transmitted. So anywhere within this region over here could be what Bob receives. So if so these balls are basically a forbidden region. So if the code word for a different message happens to fall within this region, then we'll be in trouble, right? So what you can argue with a union bounding argument is, so since 2 to the ns is a small exponential, n theta choose I will again be eventually a small exponential, L is just a constant. So overall, this volume, even though it's exponential, it's a small exponential. So the region covered by this by the union of these balls is a small exponential. So the probability of a code word corresponding to a different message falling within any one of these balls is small. So you can show that it's whatever 2 to the minus n theta cube over 32, right? So in particular, you can show that with high probability of a code design, so for most of the secrets with high probability of a code design, the code words for other messages will fall outside. So what does most mean? Most means exponentially close to 1. High also means exponentially close to 1. Yeah. So that is the sense in which we are able to prove our achievability. So with high probability of the messages and over code design, Bob will be able to decode correctly. James will not be able to will not be able to erase away all the evidence distinguishing the truly transmitted code word from some other fake messages code word. Yeah. All right. So we have, let's see, around just around 20-ish minutes left, right? Is that right? And I imagine I'll try to leave at least 5 minutes for questions and so on. So
you have 20 minutes.
Yeah. So to summarize, the capacity so the capacity of the random noise binary erasure channel is of course 1 minus p. The capacity that we've just proven is 1 minus 2p, right? And this is strictly above the sorts of bounds that are known for adversarial channels. So if you have omniscient adversarial channels, like it's known that that no rate higher than this upper black dotted line is possible, and the GV bound, the best known code constructions, are close to this lower dotted line, right? So what this shows is that the capacity that you can hope to achieve, at least for erasure channels, is strictly above. There is a cost to causality for the jammer. There is an advantage to causality for the transmitter. That is, you can beat omniscient adversaries, but there is still a cost to adversarial channels in the sense that you can't hope to get all the way to the random noise version of the channel, right? You can't hope to get to the capacity of the binary erasure channel. Because after all, he is still an adversary, he can still do this wait and push sort of attack and so on. All right, so now I'll do very briefly another example, which is the bit flip channel, the adversarial bit flip channel, which has 1 or 2 more ideas, hence this example. And then I'll try to pull together some other more general ideas to talk about the general causal adversarial channel. So in the causal bit flip adversary version, it's very similar, except now the adversary, on seeing the transmission so far, gets to decide not which bits to erase, but which bits to flip, where to add a bit to the transmission. And again, he can flip at most NP bits. Yeah. Now, in this case, the capacity turns out to be a little bit more complicated. It's the minimum over some alpha, p prime, alpha times blah, 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 right? So we'll see what these constraints correspond to shortly. So, but before we go there, so again, the 1 minus HP capacity looks like this, whereas our attained bound has this interesting two-phase regime. So for the prefix, it is 1 minus HP. So it actually meets the capacity for sufficiently small p. It is precisely 1 minus HP. But then beyond a certain critical point, like something like 0.01, 0.12 or something, then it becomes a tangent to the 1 minus HP curve. And there's a strong reason for why it becomes a tangent until it hits a quarter. So then you end up with the straight line over here, right? So that is the purported claim, the purported capacity for this bit flip version. And again, there's achievability and a converse. So the converse is kind of similar to the wait and push for the erasure, except instead of the wait, now there'll actually be an advantage to James to do what we call babbling. So what is babbling? By babbling, I mean that in the prefix for a certain length L, instead of just waiting and doing nothing, he'll deliberately add a little bit of noise. He'll add a little bit of random bit flips with some parameter p bar, okay? And then, so of course, this reduces his budget for the suffix, but for certain parameter regimes, like doing this babbling in the prefix will actually help because it increases Bob's uncertainty in the prefix, right? So Bob will have to wait a lot longer before he can list decode, before he can say, based on the prefix so far, I should be able to list decode. So so his strategy, again, he'll flip bits with property p bar. He'll pick a random code word which is compatible with the prefix, and then in the remaining locations, in the remaining n minus l locations, wherever x differs from x prime, he will flip, but only with probability half. And that's all he needs to do, right? Because if x differs from x prime, then half the time he'll flip, half the time he won't flip. So what Bob receives will be something right in the middle between x and x prime, right? So so then Bob will be confused between x and x prime. So the analysis, okay. So based on the slide, we can see where that capacity expression would come from, at least from a converse perspective. So if so in the prefix, for Bob to be able to list decode, or rather for Bob not to be able to list decode, for at least for him to have a reasonably large list size, this condition should hold. That is, the number of message bits should be larger than the Shannon entropy in the over the channel in those first L bits. So that's L times 1 minus the capacity of the corresponding random noise channel should be less than NR. That corresponds to the list decoding condition here. So this condition ensures that there's a reasonably large list of possible messages from the prefix. And then now this energy bounding condition is what we call it. It basically says that the suffix length, which is n minus L, divided by 4. So why 4 instead of 2? So if you remember in the erasure setting, we had the suffix length by 2 corresponded to the number of bits that James would have to erase to activate the Plotkin bound. Now, because he's flipping bits, but only half the time, so that's why it becomes n minus L by 4, right? And then this NP minus LP bar is just the remaining budget that he has to flip bits. So basically, putting these two things together gives the capacity expression at least the converse side of it. So it's basically saying that choose a P bar and a L such that these two can simultaneously hold, and then that corresponds to when James will have a successful attack. And again, we need to do more work to ensure that this works against stochastic encoding, and even when the private randomness is non-uniform, blah, blah, blah. But, it can be done with a little bit of legwork. Okay. Now, from an achievability perspective, the bit flip channel is more challenging for the following reason. So in the erasure setting, when James is erasing bits, Bob of course knows, this bit is erased, this bit is not erased. So I can trust this bit. I have no idea what this bit is, right? So that's the advantage of an erasure channel. Whereas in a bit flip case, Bob has no a priori idea, at least just looking at a given bit, whether James had introduced something there or not. So in particular, he doesn't know when to list decode. He doesn't know when. So he does not know, for example, if he tried to list decode at a certain point, he doesn't a priori know whether a condition like this over here holds. That is to say that the number of message bits is roughly comparable to the prefix length times the corresponding mutual information expression, right? He doesn't necessarily know that. So the idea is to do iterative decoding. So starting with the prefix, starting with a guessed prefix length nr. So he says, okay, let me try list decoding here. And then given that I've list decoded at this point, I end up with a list of possible messages. Now, based on this hypothesis that I should have been able to list decode here, if James had put no bit flips in the prefix, then I would check in the suffix and check for consistency. Check to see if any of these possible messages have a corresponding consistent code word. And consistency here again means that if there's some possible code word completion that is not too far in Hamming distance from what is observed, right? So starting with this guess, he tries to list decode and then use a suffix for disambiguation. So if this doesn't work, if in this first iteration there's no possible completion that is compatible with the suffix, then well, he just guesses, okay, maybe James did put some bit flips in the beginning. So let me increase the chunk length. Let me go forward one more chunk length. Now try to list decode with a slightly longer prefix. And now again, I'll have a bunch of messages. Bob will have a bunch of messages, maybe a different set of messages. And now again, looking at the suffix, which is now a shorter suffix, he'll try to check for compatibility with the entire suffix, like check to see if there's compatibility of any of the messages in the list so far with so there are completions in the corresponding suffix and so on. So what we can show is that the first time when this works and outputs an answer, firstly, it'll be the correct answer. Secondly, it'll be the correct answer. So James will not have been able to cause a different code word to be compatible, and the true code word will indeed be compatible. So you can show both of those things. Yeah. So basically, at a rough level, it comes down to looking at all possible sort of trajectories James could use. So one trajectory could be that James just flips all the bits right in the beginning, right? So the fraction of bits flipped in the prefix is 1 up to a certain length, and then of course it starts dropping as an inverse function because now he can flip no bits. He's used up all of his bits. At the other extreme, he could flip no bits whatsoever in the beginning, and then just flip all the bits in the end. And then there's of course the babble-and-push strategy. So sorry. So there's a particular strategy that we call a reference strategy, where he flips no bits in the beginning. So remember, our decoding hypothesis to begin with was he flipped no bits in the beginning, and then based on that, tries to decode from the suffix. Next, we assume that he flipped some bits in the beginning, and then he tries to list decode and checks for the completion and so on. So that would correspond to, so those sets of guesses would correspond to this blue trajectory. And what we can show is that regardless of what James does, his trajectory will eventually intersect this blue trajectory. Like if he uses all p fractions of bit flips, and if he doesn't, by the way, there's a separate argument, but if he uses all p fraction of his bits, then it'll intersect this blue trajectory at some point. And that's why at that point, Bob will be able to list decode in the prefix correctly, and then the suffix will match appropriately. Okay. All right, so that's all I'll say about the bit flip version. Moving on, so this I'll just very briefly allude to. So there's a quadratically constrained version as well. So Alice has a code word, but now this is a vector in Rn with some power constraint. So the L2 norm is at most square root of NP. And then the adversary gets to also gets to add a vector in Rn of norm at most square root of Nn. These get added now with the reals and so on, right? So this is, think of this as an adversarial version of the AWGN channel. And in this case, we can show, so I plotted this somewhat weirdly. Instead of SNR, I've plotted inverse SNR, so noise over power. So the blue line over here is so the capacity of the AWGN channel would be higher than even the blue line. It would so regardless of the noise power, it would be positive, but it would go down as the noise power increases. This blue line over here is the so-called list decoding bound for AWGN channel. It's half log P over N. So instead of half log 1 over P over N, it's half log P over N. And we can show that in this case, the capacity is some red line, which has a sort of weird curve, weird shape. It matches the AWGN capacity, matches the list decoding capacity up to a certain point. And then it sort of starts sloping down, but not as a tangent. So in this case, we can show, in fact, so now because even the transmitter has a power constraint, so we can show uniform power allocation for the transmitter is also not optimal. He should also, Alice, should also allocate power in a non-uniform manner, maybe more in the beginning, less later, and so on. And that's what leads to this curve over here. Yeah. All right, so that's all I'll say about the AWGN version. And in this is more, I mean, it could easily take more than the 8 minutes I have left overall, but I'll try to reserve a few minutes for questions. So let me first at least just define the channel and then try to give a sense of what the result is and what the ideas are. So just those three things. So in a general setting, again, you have 2 to the NR messages. An encoder transmits some code word. This code word could be over an arbitrary alphabet. The jammer gets to see this transmission causally and then chooses some noise vector, S over some arbitrary alphabet. And the channel combines these 2 inputs to generate the channel output. So for example, think of the bit flip version, the erasure version, the AWGN version. Like so the channel was doing different sorts of erasures, additions of different kinds, right, to generate Y. And then the decoder wants to infer the transmitted message. So yeah, so the channel takes together X and S and generates Y. So yeah, these are over general alphabet, blah, blah, blah. So again, in general, the encoder will have some power constraints. So think about the quadratically constrained version. So over there, the encoder had some power constraints. The jammer had some power constraints. And in this case, yeah, so it'll, okay, you know what, I'm just going to, so it'll, how much should I talk about this? Well, so more generally, what will matter is the joint type between pairs of code words. So think of the joint type. So the joint type is literally just the empirical joint PMF of pairs of vectors, right? So the joint type is somehow captures not just the Hamming distance between pairs of code words, but more than that, it captures sort of their given a pair of code words for a given channel solely based on the joint type, you can decide whether an adversary would be able to jam them or not. So this matrix, you don't need to know the full vectors. You only need to know the joint type. That's all that matters. And you know, I'm just going to go through the okay. So the general causal adversarial channel, we're able to characterize the capacity. So in particular, yeah. So in particular, there are analogs of the babble-and-push strategy that is basically what we work on. So the generalization of the of the push part basically comes down to this V of S given x prime. So if you remember in the push part, for example, in the erasure channel, James erased locations where x and x primes differed. In the bit flip case, he flipped with property half wherever x and x prime differed. So in general, you can mimic for a general channel, you can write down a condition for symmetrizability, which basically, depending on the channel, there is some conditional distribution V of S given X prime that James can use to somehow result in a Y that is somehow equally compatible with both X and X prime, right? From James's perspective now, the search for jamming strategies is like the search for a conditional distribution V of S given X prime, yeah? And you can write it down in terms of some equations. So there's some linear algebraic characterization that tells you when a channel is symmetrizable or not. So this is jamming in the suffix. And the jamming in the prefix, the babbling, well, that also can be mimicked by a conditional distribution. In this case, V of S given X. So in this case, James will just be looking at the transmitted bit and or symbol, and then deciding the conditional like a random noise to add in the prefix over here. So so putting these things together, then okay, the obviously technicalities that we're not going to go into, but let me just highlight this thing over here. So what ends up mattering is that in the suffix, like broadly speaking, in these things, what happens is the prefix carries the most of the weight, most of the entropy. In the prefix, you're trying to get through enough entropy that Bob can list decode. In the suffix, all you care about is that the suffix be somehow very different. They look very far apart. And you can show, because of a generalization of the Plotkin bound, that the best analog of the distance you can hope for in the suffix is that the pairwise joint type be a product distribution. So for example, if these were binary vectors, then given two pairs of binary vectors, each of having weight roughly n by 2, you would expect that having distance to be roughly n by 2 as well, right? Like the fraction of locations where there's ones here, zeros here, would be roughly n by 4. The fraction of locations where there'd be zeros here, ones here would be roughly n by 4. So the Hamming distance would be roughly n by 2. So this product distribution basically corresponds to the somehow, even if you're transmitting at very low rate in the suffix, it's the best you can hope to do in terms of joint types in the suffix. So complicated looking capacity expression, which of course I don't have time to get into, but the essential idea is, again, just a generalization of the babble-and-push setting. So in the prefix, James is babbling. And the mutual information that can be obtained by Bob in the prefix is basically going to be this capacity. It's going to be this blue thing over here. There's some technical reason for this quantity over here, which never really actually comes into play, but you can show that most of the time it's basically vacuous. And then in the suffix, because of the generalization of the Plotkin bound, then if Alice tries to be too ambitious, tries to transmit at too high a rate, then James would be able to push and confuse between two different messages. Yeah. So in this sense, we can generalize results to very general channels with some caveats, with a single state constraint. So we can only say you can only put constraints on the state symbol, like one single constraint, deterministic channel, and so on. So some technical constraints. And it's not a single letter expression, but it's not an exponential time expression as well. Like this expression, even though it looks horrendous, in principle can be evaluated. Yeah, so it's in principle computable. I say in principle, not that I've been able to actually compute it. That's an ongoing piece of work. So babble-and-push, again, I've already talked through the basic ideas, so symmetrization and the corresponding Plotkin bound. So these are details about the Plotkin bound. This is in some other work of ours, which I'm happy to highlight. Achievability, again, follows via sort of a chunk-wise stochastic code. One difficulty is here, for a very general setting, to be able to prove that you can decode, so the analog of that trajectory, like the true trajectory, will intersect the reference trajectory at some point. So we need to do some convexity arguments. That's where some of these technical conditions come into play. So anyway, that's all I'll say about that. And I promised to leave 5 minutes, and I'm instead leaving 15 seconds. I apologize. So, well, thank you. Yeah. Again, I apologize for the quality of the talk. This is what happens when you're still mildly sick. So
Thanks a lot, Professor, for an informative talk. I request the audience to feel free to ask questions if there are.
Hi, this is Shashank here. Hi, Sidharth.
Hi, Shashank.
So in the initial part of your talk, you mentioned that the capacity of the online erasure channel is more than that of more than that in the case where there's a 1-bit delay, right?
Yeah.
Is that something that carries forward to other online versus 1-bit delayed adversarial channels?
It's an excellent question. It's very hard to, like the erasure channels really, we use specific tricks to precisely characterize the capacity. For other channels, we can try to mimic that. We'd get far from tight capacity characterization. We haven't tried very hard, but uh, I mean, basically in the erasure channel, again, when you receive something, whether it's correct or not. Whereas in the bit clip version, we don't necessarily know. So from a retrievability perspective, that one single bit, it's a lot fuzzier. So that's basically one reason why we find it harder. My suspicion is that the capacity will be generally different between with even a single bit of delay. Certainly, we can show that if the delay is like logarithmic in n, then in fact you can get an even higher capacity. You can get to the so-called oblivious capacity, which is in some cases which matches the corresponding DMC capacity. So for example, in a bit flip version, if you have logarithmic or polylogarithmic delay, then you can get to 1 minus HP all the way up till there.
So what would be suppose you had to extend this, are these techniques, do you think these can be extended to 1-bit or constant bit delayed channels? Is there some kind of a bottleneck?
So let's see. So the bottleneck, so now I'm trying to remind myself of the 1-bit delay thing. What did we do over there? So we can certainly write down the corresponding code constructions that we used over there and the corresponding converse arguments that we used over there. The problem is in evaluating these things and checking whether you get any improvement whatsoever. It's non-trivial. You have to search over a large set of conditional distributions. And I mean, in principle, I guess it's doable. In practice, just haven't been able to do it. So yeah. Like for example, even for the causal capacity, right? We're able to write down a very nice looking expression, but actually evaluating that, and it is it is a search over a constant size dimension space, but actually evaluating this is a beast, right?
Right.
Even for the quadratically constrained version, like just getting that red curve that I showed you over here, took a fair bit of programming. So that's the basic bottleneck.
Thanks.
Thank you once again, Professor, for the talk. And thank you everyone for attending and have a great evening.
Okay. Thanks again for coming. Take care. Bye-bye.